In this video, we are going to talk about how everyone can design a chip, and we are going to talk about the process, about the steps, what you need to take if you would like to design and build your own chip. Correct, Pat? That's what we are going to talk about?
That is correct.
So how does it work? Explain, how is it possible anyone can design a chip?
So here's let's jump right to slide 13 there and get to the interesting thing. I started out knowing pretty much nothing and then made this thing, which is a mixed signal design, an A to D converter.
So you designed this?
Yep, I made this. Well, okay, I told the machine how to make this block here at the digital side. So I designed it like in Verilog or Amaranth, and then it spat out that. The stuff on the left here is analog, and I made this by hand. And how it's possible is basically Google was involved in getting the Skywater 130 PDK, the process on which these chips are made, opened up. And with that, the whole world exploded. And Google is now out of the picture, but things have started and it's just going. So you can do this. There's a Tiny Tapeout run right now. And the thing is, you do it at home. There's no licensing. There's no crazy anything in the way. You can install everything on your computer or even use the VM. And there it is. The atoms are yours to play with.
So you mentioned
it's really cool.
Tiny Tapeout. That's how this is basically called. This, what is it? It's not process. It's a what is it? What's Tiny Tapeout?
So Tiny Tapeout is this. It started out at the time that Google was doing the MPWs, the multi-project wafer things, where you basically could.
Click there, I think.
There you go.
Okay.
So it was like a lottery. You could design things using these open tools, but were you going to get an actual chip? I don't know. So the question was, how do we get people to be able to do their chips easily? A multi-project wafer is a wafer in which you get a small bit and can get your own chips. So it's shared, so it's cheaper. But Tiny Tapeout split that up. This is one chip out of that multi-project wafer, and each of these little squares is a project. Someone did a different project. So Tiny Tapeout ended up working with eFabless to do this more regularly and more guaranteed. It's not a lottery. You got those tiles, they're yours. So this was pure digital back in the days of Tiny Tapeout 1, 2, 3. Okay, and it was kind of slow.
So Tiny Tapeout is something what give anyone possibility to manufacture their own chip for free.
That's, well, to have a project in a chip, not for free.
So you have to pay something, or?
If you want space on the actual chip, then you start paying. If you want demo boards, it's a little more. But 5 years ago, it was $200,000. Then it went, and now you're in the hundreds of dollars to get both the chip and the demo board that you can see there.
So for okay, hundreds of dollars, and you can get your own chip on your own demo board. Okay.
So at first, you could only get one tile like this. So one little square was yours. And then with Tiny Tapeout 4 and 5, things got better, things got faster, you got more I/O, but more importantly, you got the opportunity to take a bigger slice. I think this one down here on the left, this 8x2, this crazy thing is mine. And it's a SHA 256 encoder. It doesn't really matter, but the point is you could make these digital designs and then, oh, I need more space, so you get more space. And so then finally, with Tiny Tapeout 6, Analogue came into the picture. And with Analogue, you see these squares that are all full, that's machine-filled squares. Because when you do a digital design, let's say you only take a little bit of space. Well, the system will fill up the rest with filler, decap, bypass capacitance and stuff like that. Whereas if you're doing analog design, you'd have to do that if you want it. So these squares that look more empty or that are designed funny, like this guy here, that's Uri's fetish for skulls. But the point is you could do pretty much everything. And down here, the Psi ADC, that's mine there. So this is the Tiny Tapeout 6 run.
Okay, so I think now everyone understands that it's possible to design their own chips through this Tiny Tapeout. So how does it work, this process? Like, do we need to sign up for Tiny Tapeout, or we can just start designing a chip? What kind of tools we can use. Do you have something like this in these slides? And I would like to point out later we will actually do some practical example, correct? You will actually really
Oh yeah.
show how this can be done.
I had these slides just to be able to show you, kind of give you an overview idea. But the short version is, well, the really short version is that if you get the virtual machine, and it basically has all the tools are the open PDK, the process that's being used to make the chips.
I
And
would like to
everything.
stop here because I remember from the very first video, I was not sure what exactly this means. So can we talk a little bit about what this means?
Yes. So you're a foundry. You make these chips, right? And you have developed this process, and it's a 130 nanometer process, whatever. Okay. So this was from a few years back, which is actually good news for Analog, because for reasons. So you have this thing, and in order for me to be able to give you something that you can make, because it's so complicated, you make one layer, you make another, there's masks, there's injection of charges, and you're basically doping stuff and then masking and then etching, and then so there's a ton of rules to obey. Those rules are the process. The process development kit encapsulates those rules, as well as, let's say, stuff that you could use to simulate. So all the spice models and all those things go in the PDK. So it's this big package of all the rules, the models, and everything you need to be able to produce, in the end, a GDS file. And a GDS file is a drawing. It's layers that are drawn, and these drawings represent the holes that are going to be in various masks.
Mm-hmm.
This is a hole like this, a square that I need in metal 2. This is a square I need in doped in this. This is polysilicon, whatever. The point is, it's like Photoshop. You have layers, but each layer represents one step of that process.
Mm-hmm.
So all you have to give them is this image file in some old format from the 80s, GDS, and they'll do it if it's doable. And for it to be doable, you need to have followed all those rules. And because it would be pretty much impossible for a human to hold all those rules in their head, we have tools that integrate with those and tell you that square is way too small. You can't make that square. It's physically impossible. You can draw it, but you can't make it. So in SkyWater 130, it's called 130, but the minimum feature is like 150. 150 nanometers. So if you're making a transistor and you want it to have lots of current, you're going to have a small channel, and the smallest one you're going to be able to make is like 150. So
Okay,
you
so
get the PDK.
so
Yeah,
SkyWater, that's the package of the rules
that is the
or
foundry
description
somewhere in
of
the
the
States.
technology, what
Yes,
anyone can
that's
use,
right.
basically, for example, to create a transistor or something. So basically they describe what they can do, and maybe provide even some kind of libraries, like this is a transistor, and then
Yes,
people can use it.
absolutely. When you're
Mm-hmm.
doing digital, you've got a flip-flop or something. You don't design that. It's just a block that they perfected, and it gets popped in.
Mm-hmm.
So
Okay,
so
okay,
it's
I
all the
understand now. Okay.
those are standard cells. Now in analog world, you also have the equivalent of standard cells. Say I want an NFET, so an N-channel MOSFET. Well, it's got parameters basically. You tell it, okay, I want this NFET, the low voltage threshold NFET for 1V8, and give it to me with this length and this width and this number of fingers or whatever, and whoop, you just create it, and it generates that. Magic will generate it based on the rules and stuff that's inside of it, based on the PDK, and then you have this MOSFET. And so it's partially custom and it's partially standard cell.
Mm-hmm. Okay, okay, so I understand. So basically, you need to get this SkyWater, then you need to somehow create your design, then you generate some kind of layers, and then what do? You somehow upload it to Tiny Tapeout, or there are some other companies who are
Let me
managing
show
this
you.
Tiny Tapeout, or how does it work?
Okay, so I actually did this through a beta of the Zero to ASIC Analog course, and these are basically the steps.
Okay.
You do schematic capture with XSchem. So XSchem is kind of like KiCad-E schema or anything like that. It's just you design circuits in it, except that it's very well integrated with the SkyWater PDK.
Mm-hmm.
So and it has all these functions because all those parameters. the number of fingers or the length of the channel. You can set that when you choose an NFET. You say, okay, I want this. And so it integrates well with that. And it also integrates well with the models, the ngSpice stuff. So you do capture, then you check that your circuit actually makes sense before you do anything else, because layout is so manual that you don't want to go back and forth, and you basically don't back annotate from the layout back to, even though you could change things, it gets really messy. So you want to get it really solid. And so you do that, you do your schematic, you do your simulations, then you do your layout. And this is in another program called Magic. You could use K-Layout, or there are other things, but Magic is really good and quite
There's a
integrated
good
as
name
well.
for something
This is
that
a
is
program.
creating magic.
Look, it really is, okay? The thing with Magic is it lets you do layout. Yeah, that's great. But let's say I have two pieces of metal here, two tracks going next to each other. Well, they have a certain internal resistance. They have capacitance across them. They have capacitance with the substrate, because the base of this wafer is just a sea of P, right? It's a sea of P doping. So, and it gets set to ground. So you're above that. So you have a capacitor there, you have capacitors everywhere. And Magic does magic, because it takes these painted squares and it spits out a spice with all the capacitance. And I actually spoke recently to Tim Edwards, who maintains Magic, and he was like, yeah, it'll give you the capacitance between a metal layer and the substrate. And this is related to the size of the metal layer, but also how far it is and everything. And so when you do parasitic extraction, what you're doing is extracting the circuit, how you wired it up, but also all those parasitics, all that R, that C that's everywhere. And then what you do is you did that simulation, you did your layout. This is down here, you're doing post layout simulation. That is where you compare, okay, in real life, well, as close as we're going to get on a computer, how good is this circuit?
Okay, I
Oh, there's a
understand.
ton of capacitance. That's a low pass.
So basically, you create your schematic. It's something what you would like to build, but once you do the layout, this will actually kind of add some extra components and extra things
Yeah,
which you need to then maybe have a look if your schematic is
you really
still
should.
working.
You really should. And so you do that. And then if it's just too terrible, let's say you were going into some high frequency thing and you wanted, this kind of reaction, but all this extra capacitance is just eating you away. Well, you're going to have to do something about that. And depending on the problem, you'll change metal layers, you'll shrink things, you'll move things apart, whatever it is. But then you have to go back to layout, do it again, loop. And that's why there's these little loops here in this flow chart, because you always end up going, oh no, the big loop is, oh, I have to go all the way back to schematic capture because I did it so wrong that something is terrible. But yeah, and then let's say everything is all right. I've done my parasitic extractions. I've tested everything as best I can. The layout looks good. We're ready to go. Well, what do? In essence, when you were doing digital, you would export this digital stuff, and Tiny Tapeout would take it and recreate basically the circuit, because it's just the same thing's going to come out of both processes. It's deterministic, right? So, well, more or less. But so that's one thing. Tiny Tapeout would do all the work through GitHub Actions once we push the changes. In this case, because Tiny Tapeout, because it's analog and you're free to make big mistakes, uh, you just send them the GDS. They do some extra checks through GitHub Actions or whatever, but that's it. You send them the GDS through, again, GitHub push, and it just gets sucked in. You submitted your project, you suck it in through the thing, and it gets integrated into one of these squares. Now, the reason this is possible now, the reason it wasn't possible before, is if you short out, let's say I short out ground in VCC.
No
Well,
one's project would be working.
that's right. It would be terrible. But now the little squares are gated. They're power gated. So yeah, if I enable my project and it's a short circuit, a straight short between power and ground, well, bad things will happen. But as long as it's not turned on, there's nothing. So we're getting kind of a system in place if anything ever happens like that, where it's like this one isn't easy to turn on. You have warning, don't.
Okay.
But
So what do you have on these other slides before we move to the uh, example how this is
well,
done? Because I'm very curious actually to see also how it is, how process is done. So I'm very curious to go quickly
yeah,
through
okay.
this and
So
then do the
look,
practical stuff.
in essence, there's not too much in the slides. There's stuff about me. I'm Pat Deegan, and I run Psychogenic, and I've got some YouTube videos that are, I think, interesting. This all started because the Zero to ASIC course is how I got into all of this, and that's basically these two guys, Uri Shaked and Matt Van.
I would like to point out I've already done videos with both of them and they are really good videos. So I would recommend everyone to watch these.
Yeah, they both say hi, by the way.
Thank you.
So this is the Tiny Tapeout site, and in essence, you can just go there, and I mean, there's tons of guides and resources, but in essence, you end up going to apps.tinytapeout.com when you have a GitHub repository and say, this is my repository, bloop, bloop, and it gets sucked in, and you get a little tile. And then, and the thing is that turnaround is really kind of slow, right? So I did my project for Tiny Tapeout 6. It was a big crunch while I was in Boston. And well, now I'm going to wait 7 months or something to know if it actually really works in real life. So, uh, neat thing with Tiny Tapeout is if you know nothing at all, we had at SuperCon and in Berlin, we did workshops. People knew nothing. They came in and they were on a physical tape out after 3 hours. Now, if you really know nothing, you're going to end up using Walkwe, this graphical interface to do pure digital, of course. With the digital stuff, I did some crazy things. This is a guitar tuner I did. I did that Shaw encoder, things like that. Um, and then I came to this. And so what I did was I was trying to learn how to use the tools. So Stefan Schippers, who created XSchem, did a video with Matt where he's basically doing this very sensitive comparator. And so I followed along and I just made the same thing. His circuit was available. I didn't want to take it. I just made it one at a time to know, well, how do you get a component from the library? Stuff like that. So I made the comparator, which is this blob here. And then I added stuff around it to be able to calibrate it, to be able to turn it on and off. This here, these four squares, they're one tiny capacitor. Capacitance, resistor, you get tons of MOSFETs in here, easy. You get resistors, pretty easy. Capacitors you can get, but they are tiny. There's a project where a quarter of the space in the next tape out, a quarter of the space is taken up by a capacitor, and it's 0.5 picofarads. So, I was worried about a couple of picofarads on the traces of my PCBs, and this is less than that. So, okay, capacitors, they're very small, and they're so small that I had a tendency when ngSpice, when the spice doesn't converge, when it has trouble, I would just let R shunt. You just add this option where you say shunt everything, using 10 mega ohm or something, and then it converges. Cool. Well, my system started misbehaving, and it's because the capacitors were so small that 10 meg was way too small a resistor. It was draining through it. So it's another world. The point is uh, that so MOSFETs, yeah, and inductors are just not something you want to do. They're first of all, they take a lot of space, but they're also very badly modeled. You have no idea what you're going to get. So you use RC and MOSFETs, and there's some diodes and transistors and a few extra things, but I haven't tried those.
So basically, what you just explained is how anyone can start is maybe have a look on existing project, maybe go through the project step by step, build it by yourself, and then people can extend these existing projects or then maybe start something completely
Exactly.
new.
I that's one thing with this. All these projects are by definition open source. You you put them online and then they get into the chip. So when I started that comparator, I didn't know I was going to make an ADC. I kind of decided along the way because I had the comparator, and then this yellow thing here, that's an R2R DAC. I didn't make it. That's Matt's design. He was doing that and he was testing it, and I was like, I need a DAC. And so, whoop. put that in there. Okay, now I need a block to control the DAC, and that's how I ended up with the digital side. So it's really nice because you have all these examples, and as time goes on, now Tiny Tapeout 7 is in like 4 days or something, the deadline. But all these projects are ready, and now we're another level and another level, and you can keep cross-pollinating. The thing on the bottom right here is an op amp. I just wanted to try a different layout from someone else. It has nothing to do with my circuit. I just put it there because let's try a different layouts and then compare them in real life, see if they're different.
Okay, what do you have on the next slide? Some
The next slide.
simulations.
Oh, okay. So I don't have this for, 7-9 months, but I did some simulation.
Okay.
And this is something that XSchem is really good at, simulating, but also showing the results. I find this really nice, the way these graphs are live. We can go see it in real life. But the point is, each purple line here in the graph in the middle is one voltage I was simulating in, okay, on the input. The yellow is what the DAC is doing. It's calibrating it first, and then it's searching. It's saying, okay, the voltage is lower than me. Okay, so I'll go down. So it sets the high bit first, and then the next bit, and then the next bit. And so it does this search pattern, and you can see it's a beautiful tree. It works quite well up to, the common mode rejection is pretty awful at the top there on the rails. It gets lost. But everywhere else, it's spot on. And if you see the results here, they may be hard to see, but I did these tests and I knew what I expected. I expected a perfect ADC to give me these results in white. So hex 10, 20, 30, 40. And instead I got hex 11, 20, 31, 42. That's pretty good. Down at the end here in the high, well, then it messes up. It's like F. It just doesn't know what's going on. But so this is the theoretical. And this is so it's a mixed signal design with that big block, right? Well, I ended up doing the simulation in analog. So, I mean, even a digital circuit under the hood is analog, right?
Yeah.
So this was done with parasitics in analog land, and it took 16 hours, but it worked. It ended up working. And
So
then I figured out how to do.
I'm curious. I would like to go a little bit deeper into this ADC. How does it work exactly? So you mentioned you have this comparator. There is only one comparator,
Yeah.
and you
Oh, I did
somehow.
a terrible job.
So how do you set the level what you are comparing to?
Yes. Okay. Let's go see in the actual schematic. I mean, the slides are nice, but I'll just, yeah. So let me share this the VM actually. Give me a second. Okay, you see this?
Yes, I can see it. So this is the virtual
Okay.
machine with all the tools and everything installed, which you need to actually create this chip.
That is correct.
And you can
So
download
this
this
virtual
virtual
machine,
machine from somewhere.
yep, it's on the Tiny Tapeout GitHub. It's created by Actions. This is another Uri magic thing, but the point is it has all the tools. I can launch XSchem, which is the thing we'd use to enter schematics. And this is the Skywater PDK, everything that's available. As you can notice, this is all FETs, and then this is all resistors, and there's hardly anything else. So that's XSchem. There's also magic, and there's also everything you need. So let's look at
Your schematic.
yeah,
This
I'll
is
look at the
really
test
cool
bench.
that you can actually download this virtual machine with everything installed, because sometimes just getting hello world takes ages.
I know. Getting the PDK, getting the right PDK, and blah blah blah, and then all the tools. I've done it. I used to be kind of no, I want it on my machine for real. It becomes this dependency nightmare. They've taken care of it, so it's great. So this is the test bench I used for my. Let's grow this. For the analog section. This is a symbol, not a pretty symbol that represents the whole analog section.
Okay.
This is basically the same symbol, except that it's parasitics. So this is the parasitic extraction for it. So the point of this is I can actually look at whatever the test run was, but we can go inside. So this is my analog block, all that part on the bottom. It isn't too much. It's an R2R. It's a MUX, and it's this thing I'm calling the calibrated comparator.
Okay.
That's not what Stefan made. what he made on the video was this. No, this. So we can see that this is just, well, it's a differential amp and some stuff and then this thing is basically where the calibration happens. So you tie one side to the other and it kind of cancels it out. So you're keeping it, okay, let's back up a second. This switch takes the output, this thing, and it puts it on the cap. Okay, that's that fat cap there that was on the right side.
Okay.
So it holds it there. When you open the switch again, that voltage just stays there. And this voltage comes onto this adjust thing. And this adjust thing is what sets this. So you've got P FETs up top and N FETs down. So it's like an inverter basically, but you're holding it wherever it is that the calibration wanted to hold it. So once you've calibrated, once you put that voltage on that capacitor and it's doing a good comparator job, you can count on it. So the question is, what the threshold is 1 voltage here, what I'm comparing to, and this is what I am comparing. And so on one side, sometimes I'm comparing the let's see, the input. That's a terrible name. Okay, and sometimes I'm comparing this thresh V. Right. That was because I wanted to be able to do it from internally or externally. So one goes to an external pin. So, so this is that comparator. Let's say it's calibrated. It's comparing some input signal. Now this input signal comes from, it's the thresh. Okay, so it comes from this mux. This mux chooses from the external pin or the DAC. And so what I do internally is I say, okay, you're calibrated, set the DAC to 127, high bit high. So that's pretty much in the middle. And then I output it through here and it goes to the threshold, compares to the input. Is it higher or lower? If it's higher, I'll keep that bit set. If it's lower, I'll clear that bit. Then I move to the next bit, bit 6. Set that high. Now we're at whichever voltage, that tree we saw. So let's open up that
How do you
tree.
create this voltage? You have like a resistor network or something?
Right. I've got the R2R. Hold on a second. I want to go. This is a small window.
What does it mean R2R? I have no idea.
It's a resistor to it's a DAC that's basically a bunch of resistors with ratios.
Oh.
So yes, it's an R2R DAC. So okay, let's see. Whole system.
I'm starting to understand how it works. Yeah.
Yes. So let me load all this data.
So you have like digital to analog converter, which will generate known voltage, and you compare the input to this known voltage. And
yes, I invented this only, of course, to discover that it was invented a million times, and I think it's called a SAR. It's a SAR ADC, which is, and I can't remember right now. So here's the voltage on the DAC. I set it to half. And then I look at the comparator. So let's use a line here to see what we're doing. So I look at the comparator and it says the target voltage here, this purple, is lower than me at this point. Okay, so I'll clear that bit. Then over here, why am I having so much trouble? Over here, the target voltage is higher than me. So I'll keep this bit. And then, and you can see it at the bottom here, the 80 and the 40, and it's whether I'm keeping bits or throwing them away. So at the end of the result here, I go up, down, up, down, up, down, and I kind of target the where the voltage is.
Understand.
And each run of these runs is doing that for one of these purple lines. It's going up, down, up, down, up, down. Oh, and it's kind of, it gets really close. If you look on the right side here, I have a close-up. It gets really close within the number of bits that I had access to, because it's only 8 bits. So did I forget this. Let's see the R2R. I don't know if I even have the, yes, okay. So this is the R2R DAC. It's just resistors. The beautiful thing about using an R2R in this case is that, well, it's simple. It's just a bunch of resistors chained together. But more importantly, you're doing an ASIC. You can't say I want a resistor that's 1K at 1%. You have no idea how it's going to come out. And it'll change from wafer to wafer. So there's lots of work involved in this, in matching components and getting them to values that are what you kind of expect, but you don't expect absolute values. You try to go for ratios. So this is perfect. Maybe all the resistors will be 20% greater, but it doesn't matter because 2 times that and 1 time that, it just comes out
So you
fine.
just need to use some kind of like same resistor or something everywhere, and then you will know if
That's it.
if it's not exactly what the value you wanted. It doesn't matter because they are all relative same.
That's right. Now you can do it. How did he do it? Let's see, 0.35. Okay, so if you look at this resistor here, it's got a length of 40, right? This is the R2 or whatever. Oh no, this is just the name. So it's got a length of 40. This one has a length of 20. And so that one's 2 times as big. But here's the thing. This isn't actually, now I know, the best way to do this. Normally what you want, because everything counts, and that's kind of the thing here. The course, the Zero to ASIC course, it shows you the mechanics of making these things using XSchem and stuff. But the deep down stuff, it goes really deep. So the resistor is a bit of polysilicon of a certain width and length, and it has an internal resistance that we kind of estimate to be this. Great. But you're connecting to it on the ends. And so that counts because we're down here and everything counts. So what you should do is have 1 resistor, exactly 1. And then if you want 2 times the resistance, put 2 of those. Because in theory, 2 times longer is 2 times the resistance. But in practice, the smaller you get, the more everything counts, and those little connectors count. And so, whoops, you kind of start drifting from the 2x you wanted. Now you have, instead of having connector, resistance, connector, you really should have, so 2 times that would be 4 connectors and 2 resistances.
Yeah.
But you only have 2 connectors, so that's not good. Anyways, so anytime you do anything in this, the transistors have parameters. Let's take a look at that. So just take a random NFET. So it has a length and a width. Okay, that's great. Now this is Stefan's comparator that I was doing, basically following the video. And oh, here's another funny thing. I was doing this while watching a video, right? Well, some of them are just the wrong way around. Okay, the source and the drain, yeah. But the thing is, when you're actually in the chip, at least for this technology, they're perfectly symmetric. So it doesn't really matter as long as you connect them the right way. So I didn't even do it right. But anyways, so you have these things, but you also have number of fingers and multiplicity. Multiplicity is just like having many in parallel. You want these characteristics, but you want more current to go through, just add more in parallel, and it does some work for you. Good. The number of fingers is exactly the same width and length. It'll be the same transistor in essence, if you're only thinking of width and length, but it has more gates. Instead of being one long thing, it's like chopped and put next to itself. So it has fingers like that. And so if you look at just the math, well, it's kind of the same thing, but it's not the same thing because you're changing gate resistance, you're changing capacitance and stuff. You're changing all these tiny aspects that count. And this is one of the reasons I found this so interesting. I'm mostly, well, we'll see, but you know, I do digital more than anything else. But this changes how I think about what I'm doing in ways that I still, you know, don't completely understand.
Okay, I think we can move to the next level. So once you have this schematic, I think now everyone understands you can create schematic from the library provided through the Skywater, and you can adjust the parameters of the components which you can use from the library if you would like to do that. Okay, so what is the next step? You have this schematic, and then?
So I have this schematic, and well, the next step is the simulations. So we can look at that.
Okay.
Let me take a piece of it instead of looking at this whole system, because That's too much. So let's see which pieces we have. The comparator. Okay.
How do you know all
So
these commands?
well, I'm just running XSchem repeatedly on different files here. So that's not too complicated. But so this was the basic comparator we were looking at, Stefan's thing. Now, the first thing is when you're here, okay, I have this comparator. I want to start using it in test benches and stuff. You would just go symbol, make a symbol from schematic, make a symbol from schematic. Yeah. So that gives you, something you can play with like this. Right. Now I create a test bench, and the question is, what is it that you want to look at? And the short version is, like everything here, it gets really deep. You have corners. The notion of the process has a standard deviation, right? So you can look at when the transistors are particularly fast, or when they're particularly slow, or when they're typical. And which one do you look at? Well, you could look at everything, but normally you look at what would hurt your system, right? So that's one aspect of it. The other is the spice itself. So in XSchem, you create spice like this. So what I did, oh well, before the spice, this comparator is the raw comparator. It needs extra signals to calibrate and do things. So instead of, I just want to look at the comparator here, I just imported these things, and they're not really anywhere in my layout, at least at this stage, but I need them internally. I need this inverter here to do something, to turn on the pass gate. I need the pass gate to do the calibration, stuff like that. So that's one thing. The other thing is, so you might notice, well, look, you want to do some spice. Where's VCC connected? Huh. What's controlling the start? Okay, so XSchem has this system that is basically a stimuli editor. What it does is it has, unfortunately, its own little language, but it's basically a way of creating, in Spice, do you know there's voltage sources, right? You can have a DC source or a sine wave or stuff like that, but you've got the PWL, right? Which is an arbitrary waveform. You can do whatever you want with that. It's just at this time you're at this voltage, at this time you're at this voltage. It's great, but it's horrible to create. So this, basically, you say, okay, I'm going to set these voltages, set start to 0, set start to 1, logic 0, logic 1. And then you wait this amount of time, set it to 0, da, da, da. What that does is create a stimuli file, this thing. And we can look at it. We don't usually have to look at it, but we can. Where was I? Nope, that's bad.
So it will create the signal which you need.
Yeah, that's right. So we were looking at the comparator. Okay, this guy. Stimuli, TB, comparator, SIR. So this spits out spice, which is these V, and okay, so you don't really have to care about this. I'm just showing you that you set these commands and you say, set the signal high, set the signal low, and it'll just deal with that with it for you. And it's much better than trying to do this in Spice. So I have that, and then I have my actual Spice, the thing that I care about. And what I'm doing here, I can't say that I actually remember, but I'm including the stimuli because we need those voltage sources. And then I'm doing a few runs where I'm looking at this at different temperatures. So I'm saying the temperature is nominal 40 degrees, and 30 degrees is one standard deviation away from that. Give me a bunch of different temperatures and run a few times. See how much everything spreads out. So once you have your spice and all your stuff, you just basically go, oh, sorry,
play. You need to play. Yeah? No? Is there play button?
Yeah. So you say netlist, and then it's complaining because it doesn't know that I used the stimuli file. Simulate, it launches ngSpice, and then now it's doing all these different runs. And you can see the temperature vary here, 19, 65, 53, 15, minus 54, ouch. Uh, so it's going, and I think I did 20 runs. I can't remember. Once that is done, so what I was doing in that spice was writing to a file, all the results. Now I can just load these. If you look in here, this is just an xschem command to load the data. And finally, there we go. So the plus and the minus are represented in this top graph. I set the plus to this, I set the minus to that, and this is the output of the comparator. And you can see that these are a bunch of different runs. Here's
Based on
one.
temperature.
Yeah, so at different temperatures, we're getting different results, but they're all agreeing, except maybe this guy here is not so great. So that must have been, I don't know if it was hot or cold, but it was extreme. So I have my test bench. I'm
Okay.
happy. The circuit is good.
Okay.
What do I do now?
Layout.
That's right. And so I don't want to, some people actually go into layout and they look at their circuit and they basically do everything by hand. Okay, they choose every transistor by hand, and you can do that. And I mean, these are experts, so there's probably a reason. This is not what I want to do. So what ends, oh, I killed it. So you can export a net list from this thing, comparator. So I got this out. I exported that, and it's just this net list here. So I'm going to not. There we go. I don't want to mess up my system here, so I'm just moving it over.
I was exactly thinking about it.
So if I start Magic with a, let's call it comparator.
Magic Sky.
I'll give it the same name. So this file doesn't exist, comparatorstefan.mag, but if I start Magic with it, yeah, I used this shortcut called Magic Sky to be able to get the Sky technology here loaded. I don't know if you can see that. So Magic has basically 4 tools that you always use. This DRC box tells you in real time if you mess up. This, how zoomed in am I? Okay, I'm pretty zoomed in. So this grid here should be at 50 nanometers. So if I just take this square here and ask it how big this box is, yeah, so 50 nanometer box, right? So let me paint this with metal 1. Now, see all this white stuff? The DRC went up. Oh no, we messed it up. So Magic knows what the problem is. Now I want to know, so I can say DRC Y. And then it tells me, hey, that metal box you made, yeah, you could paint it, but there's no way I can fabricate that. The area is smaller than than 830 micrometers squared. So if I want to get rid of my DRC, I either get rid of that or I just paint a bigger box and we should be fine. There we go. DRC back to 0. So DRC is tool 1. My mouse is tool 2. This box here that I move around is where stuff I do takes effect. And this console down here is my very close friend where you can add commands and do stuff. So I'll just say paint metal 2 and it happens in the box. Now I customized it a bit so that lots of stuff works in a way that I find more agreeable. What's happening here? But that's the point. So we wanted to lay out our comparator. Let me erase this and zoom out a bit. Oh, I see I'm in caps lock. Okay, let's import that. Magic has an import spice. So you can go here, and here's my spice that I spat out from xschem, and I'm just going to do this. Bloop, 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 bloop. Stuff is happening.
You will be out of your silicon.
I don't know if you see all these messages coming up here. I've got a bunch of DRC now, and I've got something to show. So it found those input and output pins that I put in, the plus, the minus, all of that stuff, and it has created a bunch of MOSFETs for me. So these MOSFETs, let's look at one. They have the width and length as specified. They have the number of fingers. Actually, these are all multiplicity one, fingers one, but they have all those specifications. This thing here, this and this is the gate. The red is poly, so polysilicon, basically resistor-ish. It's contact, but it's not very low resistance. This is the gate. These dark blue things are the gate and source connectors. So here and here. So which one is the gate? Which one is the source? You get to choose. Now, here's something that is really sad, though. So I have all these things, and I can see that this is XM7.
So these are the components.
Okay. They're the components.
Yeah.
And XM7 is my MOSFET 7 there. But what's it connected to? Who knows?
But you imported netlist. I was expecting there will be some wires.
Yeah, I know. If this doesn't get done soon, I'm going to do it. Some way of knowing what gets connected to what. Because Magic is very nice in terms of being able to script it and do stuff. I've added tons of commands and things, but I haven't done that yet. So short version is, what you end up doing is looking at the schematic and coming in and placing your stuff accordingly and basically routing manual style. So if I was to route this, I would say, okay, these two things are the gate. I probably want to connect it on both ends. And so I just start a square here, let's say here to here, and then paint it with metal 1. And you can paint with this here, if you find metal 1, like that. And then from there, you can basically copy anything that's around. So this will be metal 1, okay. And so now I have this, and it tells me what's electrically connected. So if I zoom out a bit, you can see I'm connected to this and this electrically. And so now you route everything. Now, either we can do a little tour like that and look at various things, or we can start fresh, but
yeah,
otherwise,
let's so basically we covered the basic steps or how this can be done. So I think everyone understands how this can be done. We had a look on more complicated example. And now the example what we are going to do is something a little bit more simple, I guess. And,
yeah, let's do something more simple.
And it will help us to understand the complete process.
Right.
Okay.
So I will, what do you want to do? We can do something dumb, like super dumb, like an inverter, or something a little more interesting, like a pass gate. I think an analog switch would be fun because it's got different kinds of FETs and it has hierarchy to it. We do like a pass gate and an inverter, wrap that up, and then just export it. How are we doing on time?
We have maybe like 1 hour.
We'll do it quick.
Okay.
So what do you want to do?
What we can do in 1 hour.
Okay, we'll start with an inverter, and if it goes well, we can do the whole pass gate, and if it's complicated, well, we'll stick to that.
Okay, let's do inverter. I think inverter is good enough to show all the steps.
Cool. So I'm going to save this as inverter.
So how did you start new project? I didn't see that.
I just launched Xschem. Okay, here we go. I just launched it without saying anything at all. Just hands off. If you say nothing.
For example, in a directory, in the project directory, Robert.
I created an Xschem directory with nothing in it. I don't think there's anything here. And just launched Xschem.
Okay.
So I want everything to be in this one place for my schematics and test benches and all that stuff. So I'm just going to create a new file. And unfortunately, it's called untitled. And if you don't save as something, you'll end up saving it called untitled, which is really annoying. So inverter.
Okay.
Okay. And I say it's annoying, but Stefan and all these people, it's happening right now. He responds like that to any kind of request. So I should basically just talk to him or do it myself. So I want to add, we need a PFET and an NFET for an inverter, right?
Okay.
So here's, I just did insert a symbol. I've got a few places to look. This is the XSCHEM library. It has fake stuff. It has I/O pins. It has meta information. It has voltage sources and spice kind of things. Okay, these aren't real. They're just useful.
Mm-hmm.
So the first thing I need is some input. So an I pin, right? Because I want to label these pins.
Mm-hmm.
So here's a pin. So we're going to have a VCC, a VDD, and an input, and we're going to have one output.
Okay.
So I added this pin. We'll call this VCC. I'll copy it over to... The sharing is making my thing a little laggy. I'm sorry. So now I've copied it twice and thrice. So I'll call this A, and this will be VSS. So this is the, our power. Now I want the output. I could go in there and get the O pin, but whatever. XSCHEM is pretty nice with this. I can just change this here live. Okay, so whatever. Put that there. Now we've got our meta information, what comes in, what comes out. We actually need some FETs. Unlike the XSCHEM stuff, this comes from the actual PDK because it's PDK dependent. So there's some stuff in here, but basically what we're looking at is this stuff. Capacitors, diodes, like I was saying, there's lots of FET choices, lots of PFET choices, resistors, and that's it. You don't really have much else here. So we can go with classic or low voltage threshold. Let's use that. So here's my N. And I need a P as well. And we'll match them. PFET, LVT. And the P goes on top. Excuse me. Yeah. Okay. Is this good? We could set the width and the length and all that stuff. In essence,
No, don't. We don't need to do that.
There's no point here.
Yeah, so these are the parameters which you can adjust. I just would like to go through the steps as quickly as possible.
Oh, okay. Okay, so the output is going to come out here. The input goes to the gates here. And so now you just wire it up like you were in KiCad or whatever. So the keys are a little different in theory, but in practice, I basically mapped everything to be exactly like KiCad, and life is great now. So let me readjust the screen. VSS down here. Whoops. I copied it. Okay. Now notice that, oh, what is this? Oh, yes. Okay. How did this happen? I'm not too sure why VDD is set there. So I'm going to call this VDD.
Okay.
Because there are 3 and 4 terminal devices. I don't quite understand how I ended up with that. But the point is, okay, I need a label for this guy. Well, I'll just rewire it. We want to go quick. So I need to connect the body because MOSFETs are 4 terminal devices, right? So I want this. Oops. Oh, come on. Forget that. Okay. Now, finally, these guys are connected, and this is where we get this from.
Okay.
That good?
Yeah.
Reasonable. So, I've got my file. Does it work? Let's find out. What I need is a symbol from this. Well, yeah, let's do it right. So I'll just create a symbol, bloop. Yes, I do. And now that's done. So let's do a test bench. Save. Call it TV inverter.
So you create the test bench also in the schematic.
Yes, in the same place, except that I just wanted it. I could have done these tests in that file. It's simple enough that you could stick your spice in there, but this is how you'd normally do it. I didn't look at the symbol. It's not really too beautiful,
It's okay.
but that's okay.
Don't worry.
Okay, so this is my inverter. Does it work? Let's, well, actually, yeah, we have a way to do this really simply. I'm going to add some spice stuff. So like I said, this is going to be from the XSchem library, and the V stuff is at the bottom. So let's just add a V and call it 8. Pardon?
No, it's okay. I was sick last week, so I still have some cough.
No problem. Okay. With spice, you need to have something that is a 0 net or a ground. So rather than call it VSS, I'm just going to call it ground. Let's stick that here. And no. What am I doing? What do I want? Label pin. Call this VDD. Make a copy, bring it over. And now the input and output, what do we use? We'll just use, let's use a sine wave. Make it messy. So I'm just copying this. I'm going to copy all of this. Oof. Yeah, I'm laggy. I'm sorry. Virtual machine, Zoom, etc. So, yeah, forget the labels. We'll just bring it down. Stick this to here. And the output, oh yeah, not 1v8. So what would it be? Sine around 0.9, 1v at 10 meg. Do we need parentheses? I can't remember. So I'm going to add a resistor here. See, I'm adding it from the XSchem library because I don't care. This isn't a real thing. I just want to have a load on my thing to make simulation a little bit more certain.
I'm very curious what's going to happen.
Okay, let's call this something out. Oh, and I should put a label on the other one. Click, give it a name because otherwise it'll be node something weird. In. Okay. All right. So that looks like something that might work.
We will see.
We will see. So let's look at the net list. Okay, so I'll generate it and you can always look at it or edit it. And so what I did was generate that net list. It gave me my voltage sources. It gave me this stuff. Now I could have made mistakes. It's not doing any checks. ngSpice will tell us. Oh, and I don't have any spice. That is important. I have a net list, but no spice. So one thing that really is required and kind of odd is this corner stuff. It includes a bunch of things for you and just makes your life generally easier. So
you just copied this. Yeah.
I just copied it. I stole it from the example that loads when you do nothing. And what it is, it's saying I'm using typical, and it will include a bunch of sky things for me, and it'll just deal with lots of things that I don't have to care about. The final thing, I need some spice. So from the XSchem, I think it's called Code. Yeah, Code. Well, let's do the shown just because that way we can see what we're typing. And yeah, so spice. This blah blah you need to replace with something. And let's see. I put some examples on the side just to make sure that I wouldn't have to think about this too much. Doc. Splice, what's this? Oh no, that's all my files. So, right. Sorry about this. Yep, that's not working out here. Right. You want to do a bunch of temperatures, say? We'll do that.
Okay.
So I'm just, copying this stuff because some of it is incantation style. I'll get rid of the R shunt. That's a problem. So I'm slightly, let's not do that. Param VCC, we don't need this. The temperature is this Gaussian function. Damn it. What have I done? What have I done? Okay. The temperature will be varied if we put this on. And get the delta. So the control block here, we're just going to run a few times. Get this.
Okay, so these are the parameters of the simulation.
Yeah, this is actually the control of the simulation.
Okay,
So
control.
I'm going to write a file called tbinverter.raw, and I'm going to loop do while, let's say, run smaller than 20, okay? And we'll do a transient analysis of starting at 0 of, oh no, that's, so if you're familiar with Spice, you basically give it, how fast are we going? 10 meg. You give it a smallest time step and a time to run. So let's go for 1 millisecond. Let's see. And then plus 1. Yeah, this isn't the best GUI for doing this stuff. How do I end the while? Just end. Okay. And then I'll comment out quit 0 so we can look at it and see. Okay. Do I need a dot? I do need a dot. So here's my spice. Boom. Let's back up a bit. Okay. Now if I do the net list and look at it, it will include my little control block here where I'm doing a run. I'm doing a DC operating point analysis, writing that. Oh, I'm not writing all my stuff. Okay, it's good to check. We also need to write this data. So we do a transient analysis. We write the data. And I'm a little bit superstitious, so I always end up going set append right because I'm not sure if it forgets. And that's it. So netlist, let's try this simulation, see if it works. Now that quit 0 that I commented out at the bottom, it would have made this window disappear and not tell me that, oh no, something is terrible. Something is wrong, error online. Okay. That PFET that I was suspicious about, I think it's weird. So let's go in there, get rid of this PFET and put one that I actually know. So PFET. Oh, it's because I used the 3, didn't I? The 3 is a 3-terminal device, and it's supposed to make things easier, but yeah, I'm not a big fan. So let's just wire this up to this. so that the body's on the right potential. Now we can back up. Oh, I didn't do that right. Recent. Do the net list again. So that way we take account of the change we just made. Let's see if that helped. Yeah, we're running. Okay, now the runs have happened. We've got a bunch of rows in each of these transient analyses, and they've all been written to this TB inverter raw file. I can get rid of this. Now, XChem lets you see this stuff pretty easily by saying, where do I, oh, graphs. And things have moved recently. Add waveform graph. Let's put it up here. And also, I need a way to load this data. So graph, add reload launcher. Now, based on the name of my file here, which was TB inverter, it pre-filled this with TB inverter. So that's great. That's one reason to do that, to write the file with the right name. Now, if I load the waves, well, nothing happened, but that's because we didn't tell the graph to do anything in particular. So if the waves are loaded, look at all that. On the left side, you can see all the signals that were saved. So all we care about is in and out. I'll add the in, I'll add the out. And wow, that's pretty messy. So let's change this color to red. Are we inverting or not?
I have no idea.
Let's find out. I am collecting too much data for this speed. Let's shrink this. Yeah, because my computer is slow to respond right now. And hello.
Yeah, I can
Sorry
hear
about
you.
that.
I can hear you.
No, I'm sorry. It wasn't you. I was talking to my computer here. Let's not collect this much data, and let's
But
shrink
it was
the time.
inverting. I could see it.
Yeah, but did you see how small it looked? So 100N, and we don't need 1 millisecond. Boy, 100U. Let's redo that, and it should actually run faster since we're, oh no, I changed the step as well. Okay, maybe 20 runs was a little bit excessive at this point. Reload this data. Okay. Now, something is weird with our circuit because it's not acting too well. The input is going up to 2 volts, but the output is just floating around here. So did I get my inverter wrong somehow? Okay, this is okay. I think it's, my sine wave is okay, right?
Maybe it's too fast. Maybe make it slower.
Slower. That's a good idea. I'm also going to check. Oh no, we know VDD is fine, but I just want to see it.
Instead of 10 meg, just put there 1 meg. I don't know.
Yeah, okay. Let me just check VDD. VDD. Yeah, that's where it should be. And the sine wave, 10 megs should not be too fast for this. But 1 meg. I said I'd do the quit, huh?
Okay.
Look at that. This is why sim is good. Oh, this 1K. Nah, it's fine.
Oh, maybe, yeah. Too high resistor. Too low, sorry, too low.
Yeah, but you know.
No. Oh.
Okay. How about a meg? See if we get everything. Okay, well, I used the LVTs, right? Maybe they have something of interest. And the smallest, yeah, there we go. Now we're inverting. Okay, let's give it a little bit more granularity and a little less time. So 10 nanos and give me 2 U's. And I want to quit because I don't want to keep closing that. Boop. Net list. Simulate. Da-da-da-da-da. And then reload. Did I do something wrong? Oh, I shrunk the time. Look at those beautiful transitions.
Go.
So we can see that as it crosses over, and it rises up pretty nicely. Wow, I didn't know that that was way too low a load. Success. We have an inverter, or we could switch it out for non-LVT and see, but let's say we're done and we're happy with the system. It's time to move on to layout. So maybe it's good we just did the inverter. Okay, so what I need now is that spice in a format that is a sub-circuit, because you saw that spice, it's just spice and voltage sources and stuff. But I want to come in here and get a spice that is just a sub-circuit. So LVS netlist, top level is a sub-circuit. I checked that. Netlist. Now I got that netlist, and let's see, where are we? We're in XSchem here. Now in simulation, we got this thing. So if we look at it now, if we look at it now, we can see it's a sub-circuit. Cool. The order of the pins is sometimes problematic, but whatever. So now in Mag, we've got the stuff we played with, but I'll just go Magic Sky. That loads my Sky stuff. What are we calling it? Inverter. Mag. Now we do that same thing. File, import spice. Get that spice from where it was, which is in XSchem simulation. Okay. Now we can zoom out. Now we have our two MOSFETs. I, U, and U. And now we want to do, what we want to do is look at, keep an eye on the schematic, this guy. So M2 is the P that goes up on top, and M1 is that one. So not too complicated. What I do is I basically grab them, and you can see we have a bunch of DRC errors. And one of the questions is why? And if you look at it, well, we've got DRC errors on the gates here. And that's because they're just too small. Those squares are too small. But it won't matter once we start wiring things up. So all you have to do is find a placement where you're happy. Now, that's, for me, a bit of trial and error, because if you get too close, you start getting DRCs everywhere. So I just want it as close as possible before I get extra DRCs. So I'm at 12. That's good. So what do we have? We've got VDD, this guy. And, you know, by tradition and just cause I like it on top. VSS, this guy. Put him on the bottom. Well, bottom-ish. And a few of these programs, you see the refresh is a little bit funny. A is our input, and it goes to both gates. So I'm going to stick it here. And Y is our output. And I'll just put it there because it makes sense. So wiring it up, VSS needs to touch whatever it needs to touch in the schematic, and it also wants to touch this guard ring. And so same thing for VDD with this guy, because that's what basically is touching on the body. Okay. So how you wire, well, there's a few ways, but in essence, I like to start with squares just because I have more control. And VDD and VSS, we can be generous with, you know, and make squares like that. So important things are gates. So what do I need to, these two, okay, this will be, where's my XSchem? This side, we're going to mirror it like this. Where they're touching is going to be on the left, and yeah, on the right, sorry, and the two gates here. So one of the sides goes to VSS and one of the sides. So this is a very simple circuit too. We're just going to bring this one up, bring that one down, have the gates come in from A, and have the two ends here connect to Y.
Okay.
So all we have to do is, pardon?
Let's do it.
Let's do it. So we make a square. And now I need some metal 1 because that's where my connection is. And then I can use the wiring tool. Oop. Now these things, see that DRC went away? And that's great. I don't want this. And I also want it connected to this gate. And we're going to be really lazy, I think, and just connect one side of the gate, whereas you should connect both. So now that's connected, and I can wire it up here. And if I look, you can see they're connected now, right? And then the two outputs go to the Y. And so we have more space here. I can give it a big square. Now, the advantage of a big square is that you have low resistance, right? The disadvantage is that you have high capacitance. So it's all trade-offs.
Hi.
So these, pardon?
Hi. Not for real capacitors. Real capacitors, you need real capacitors and it's still low.
Yeah. Okay. I'm not doing a very good job here, but it's a job.
So how do you know it is connected in the Z direction?
In the Z, how do I know? It's this squiggle. Well, actually, how I know is because when I select one of these metals and I go around, see it selects all the gate.
Yeah, I know,
So,
but how did you know you need to draw on the
yeah,
layer 1 or what was it?
because, okay, so these blue things are VLE, which is, so light blue is the local interconnect. It's like a very bad conductor. Okay, it's on the bottom there. On top of that, you've got metal 1, and you can touch those with vias through this VLE, this thing here on the right. So wherever there's VLEs is like, hey, connect me to metal 1, please. And so good. So that's all I did. I said, okay, this is the drain. I want it connected to Y here. And so I'll just put some metal 1.
So if you would like to go from metal 1 to metal 2, then you use different kind of via?
You use another kind of via. So you've got metal 2 here, and you've got M2 contact. Now,
Okay.
there are rules about how much space needs to be around the vias and da-da-da. So really the easiest way to do that is to take a square here and then to go in devices and via 1. Via 1 is 1 to 2. So if I do that, I get this, and now I can connect to metal 2. But I'm going to undo this, and notice how many undos I do. 1, 2, 3, 4, 5, 6, 7, 8. That was the amount of undos. So that's what that command did, which is why it's nice to use. So the two Ys are connected. We need the VSS connected to one of these sides and this body. So let's do that like this. I'll just give it a big plane. Oh, I can't do that. This gate's going to get in the way. Oh, look at that. And the gate is actually causing us problems here because it's a DRC error, right? So we really do need to connect it. So I guess I will. So this will give us a chance to escape, I guess. Let's escape. Let's get out of here. So I have to get down there and I have to get out. So I'm going to paint this in metal and then go to layer 2. Like, oof. I'm going to grow this box. Okay, grow it. So exactly what I did there, the via 2 or via 1. Via 1. And it didn't want to because my box is too small. Again. Okay, finally. So I'll be able to get out of there with metal 2 and go to some ground. So metal 2, pop. Just pipe this out. And now here I want to come down. No. The crosshairs are really useful for knowing, okay, I should turn here. Whoop. And we got rid of that DRC. And we're going to have to do the same thing up top. let's call it. Okay, 2 gates. So now all the gates are connected. Whoops. Okay, and finally we can do VSS. So let's get to here. Now I did it the hard way. You can also use the wiring tool. Whoop. Now I just went down a layer. Whoop. It's just all about mouse clicks and stuff. So let me get some VSS on this body. Whoop. Too close. So you notice that those you get really sensitive to those little white those little white sparkle things because they're like, you're in trouble, sir. We have 2 DRC errors left. I can't remember what is that. I'm not too sure, but I'm going to paint some VLE here, and suddenly now the body's connected, and so is this side. Whoops! It looks like I'm connected to the gate too. I am. I'm not sure how, and maybe we'll leave that error just to show it. Okay, the VDD also has to go here, and I need to find my DRC error. So this comes here. So now that's connected. Oh no, it's not connected yet. Need to add some vias. Move this box here. VLE, pop. And I think I created more DRC. Pop. Did I just add a DRC? Let's find the next one. Ah, okay. So this corner, a little bit like PCBs, you know, it's not happy with the etching here, but here it just won't let you do it. So we can grow this and it'll be fine. It'll go away. So let me do that. Boop. So that's one less. Now where's the next one? Oh, yes. So I did do too much VLE here. I'm not sure if it's, we can look at why exactly. Let's see why. The overlap is too small. Oh, huh. Maybe I need to grow it rather than shrink it. So I'm going to add this, and I'm going to add some metal 1. DRC 0. Okay, now I think we have a problem, though. I had the impression that the gate was connected to this VSS, and I'm not sure how that would have happened. What is this? What is this? How did that appear? Well, it's a good opportunity for erase M1. Flop. Okay. Now, of course, this is paint. These aren't objects, right? So if I erase metal 1, it's erasing all the metal 1 in that little square. It doesn't care about anything. So you end up being able to do interesting shapes, but also it's just paint. So we have all our gates connected, and VSS is connected to the body on that side. And, oh, forgot VDD. Need to escape that, and we'll be done. So let's get out of here. Actually, I should grow this square. Boy. Like this. Oh, come on. I still haven't mastered the commands to, you know, change the square's shape too well. It's tougher than it, well, it's tough for me to remember. So let's go up. Oh, wrong window. Let's go up a layer with VIA1. Boop. Let's make a metal 2 square here. Metal 2. Boop. And now we can come down to metal 1 like this. Yeah, so there we go. So now the body and that side, the drainer source or whichever that is connected to VDD. So I think we're done. And boy, I didn't save a single time during all that. So I'll do it manual style. So now it wants to write, see, it has this Sky 130. That's not the name of our file. But when it imported those things, it customized them. So it creates these Sky blah, blah, blahs and FETs. And the blah, blah, blahs are all your particular settings. So I'm just going to write that. There's only one really. there are two. Oh, there's a pfet and an nfet, and this is my file that I'm saving. So normally you just say auto write and it spits them all out. If we look at the directory here, we basically now have this sky stuff in here. And I still don't know how to move that to a separate directory. It gets really noisy. Anyways, so we have our magic, we have our layout. Great. What do we do with this? Well, this is a very small project, but first off, we want to look at the parasitics. So there's a bunch of voodoo for that. Obviously, as soon as you're in that wiring mode, if you stay there, you'd make these mistakes. That's how that other thing happened. So the parasitics, if I look in my home, I saved these voodoo commands here for parasitics. It's all of this. You have to say all of this to get the parasitics. I didn't want to do that, so I put it in this file, and then when I launch Magic, it just imports that stuff. So we can basically now say parax extract, and it becomes a command. Magic is really easy to extend in that way. So I'm going to do this, blah, blah, blah. Do you want to delete it? And yes, I do. Goodbye. Yes, yes. Okay, now we have all this new stuff in here. And if we look at inverter parax compared to xschem, the original spice we got there, inverter. So, oh, it's not much different. There's not too much capacitance, but this is our original 2 MOSFETs connected. And now we have this, and apparently, oh, I'm not looking at the right file. I'm sorry. .spice. Spice. There we go. This is the parasitic extraction. So there's our 2 MOSFETs, and now resistances, and some capacitance. We even go up to a whole femtofarad between a couple of these things.
Okay, so now this is basically the physical circuit. This is not the theory, this is the real circuit.
As close as we can get, yeah, this is the real thing. This is all the tiny, I mean, these resistances, some of them are really tiny, some of them are not. Some of them don't matter, some of them do.
Can you simulate this?
Yes.
Okay.
So let's say we take our test bench and we go back to it. And was I in the test bench here? Yes. So let's add this again. So I'm going to copy all of this.
And we can compare the results?
Yeah. Of course, I didn't make it, well, I made it kind of horrible. I don't know how different they will be. So let's get rid of this. Oh, no. I just want to get rid of this. I don't need another voltage source. I just need new names. The in will be the same. The out will be out parax. Okay. Now, this isn't quite right because this is just doing it with the same inverter again. So instead, what I need to do is some magic with xschem to say, hey, first of all, let's get this parax spice and copy it over somewhere easy for xschem. And then, yeah, I always forget this, so I saved it. Now, here we go. This was for my mixer, but we'll just adapt it. Now, if I add these things, I'm saying, what was it called? It was called inverter parax. And so we'll just get this. It's called sim.spice. I think it was just spice. Again, like that. Okay, now, so this, if that worked, no, I didn't get it right. Inverter parax, that's spice. Oh, I put it in simulation, didn't I? So this is a good test. If I control click on this, it should load that. So because this isn't a real device, normally if you do a certain command here just to enter it, you go and see what's under the hood. Here there's nothing under the hood, but a click will show us this. So now we can run this. Is everything okay? Everything looks okay. If I do netlist and simulate, and we can make it worse if there's no difference here. Oh, it's not happy. Job not started. Nesting of subs. Oh, I'm still doing the LVS thing, I think. This. Pop. Netlist. Simulate. Load these waves. Now, nothing has happened because we didn't actually include that signal. It would be called out px, and it is exactly the same. So you want us to...
no, that's good.
Okay, so that's there. Now, yeah, our inverter is performing beautifully. So good job. Now we're basically done. So what would happen in real life is, well, one more thing, because now I have an inverter, but it has nothing to do with the shape of the Tiny Tapeout chip we're going to make. The chip needs to connect to the analog side somehow, and it needs to basically know where that is. So there are files that we can download here. Let's see.
So we have to somehow connect our circuit to the Tiny Tapeout.
Yeah. So that's what this TT block thing is. Where's our stuff? So if I go into here, now I've got this def file, whatever it is, and it defines where the pins must be, basically. So to connect to within that whole mux thing, the analog and the digital mux. So if we launch Magic yet again, but this time with our, here, Robert.mag. Now I have an empty project here. I will do def read TT, whatever it is. And now it has read this file, and suddenly, look at that. We have pins here. These are the analog pins. And then way up there. So this is the square we have basically from here to
So these
here.
are the pins which are connecting the block which is available for us.
Exactly. So up at the top are the digital things, and down at the bottom are the analog things. Yeah. Let's see. It's so... I'm still looking how to change Magic's background from this gray because I can't see nothing. Anyways, these are the analog pins. So now this would be, we could submit this as is to Tiny Tapeout, and we'd get a project that does absolutely nothing, but it would still be good.
Now we have to import our inverter here.
Yeah. So all I have to do now is cell place instance, because we created this cell and we have our inverter. Flip. It's very, very tiny. This would be a sad project, but if I can look inside here, bloop, there's our inverter. And all I have to do now is connect into one of these pins, out to one of those pins, and VDD and VSS to power rails. We could do it, but let's say we did, okay?
Okay, so the power rails are one of the, where they are, because you say on the top there are digital, on the bottom analog, so where are the power rails?
There are no power rails. They're basically up to you. You have to make them. And I believe the rule is it has to be 95% or more of the length of the height there, and between something and 2 micrometers. So I've got my box here, and it is 210 microns high and 9 wide. So I'm just going to adjust it. So you say box size 2 UM, 210 UM. Pop. Okay. So this is a good size for that box. Now I'm going to paint it with metal 4. And then you would call it V ground or V power, depending on which one you want. And so you set a label, create a port. We can do that. But the point is you call it that. And then you have another one for V ground. So you get 2 rails, and they're on metal 4 both. And then what will happen is you're not allowed. There's actually 5 metal layers. You're not allowed to 5 because Tiny Tapeout routes power there, and every time it sees one of these rails, it'll drop some vias for you. And
Mm-hmm.
so
Okay, so
appropriate
you
name.
don't connect it to any pins here. It will be connected in the next
You just
step
give it a
when.
right name,
Mhm.
V power, V ground, and then that's it. It will come from the sky and just be delivered to you. So, but the important thing is that you have to connect these to your circuit.
Okay, okay,
That's it.
okay, I
And
understand.
expect it. So
Okay,
connect this to VDD, that to VSS, into one pin, out to one pin, document your thing, and then, oh, and then, right. So GDS, right, yay, .gds. So if we look in here, we now have a yay.gss, GDS, and let's load it in a completely unrelated program. So this file, along with a left that you'd produce, is what you stick in your repo, push up, and then you're done. So this is our beautiful project. It's this square
this
with all those pins
GDS,
and
yeah,
stuff.
that's the file what you upload to the
That's
GitHub,
it. That's it.
and it's
And
finished.
that's the whole thing. We're done. I mean, you should document it. My but I mean, we went through the whole process. All we made was an inverter, but oh, there's one thing we didn't do that you really should be doing because yeah, we got it, but did we actually wire it up correctly? Mm-hmm. So if I go, I think this should work. Inverter, make LVS. No rule to make target. Okay, yeah, I forgot about that. So LVS is layout versus schematic. And the question is, did we actually wire it up
Oh
like the
yeah,
schematic?
I know what you mean. If the all nets are connected correctly.
So when I'm doing a DRC in KiCad in PCB new, it checks the schematic and for equivalence at least. In this case, we could have wired it up completely wrong. No DRC errors, but the circuit just doesn't work. So what you do is let me not do this, but show you what the command would do here. It would basically run this LVS NetGen. So there's a program called NetGen, which takes in one circuit, so layout, and the other circuit schematic, and maps them together. And it's really pretty smart. If you have a resistor that's 10K in your schematic and a series of little 1K resistors in there, it'll jump, merge them and say, okay, that's the same. Because source and drain are symmetric. Well, it figures it out. So it does LVS, and I'll show you a good run with my project, let's say. So what is this?
It is actually quite simple. I didn't know it's so simple.
It's when it's
I mean, the
you're
process is
having a
simple. I'm not
problem.
saying the doing the design is simple.
No. Well, it is surprisingly simple, and I mean, these tools really give you access to everything you need to know. So we just did the whole thing. I mean, the LVS we can talk about, but the point is it's not that complicated. It comes out and it says these match uniquely, and okay, I'm good. And so you post that up, and now suddenly you wait till the baby is born, but you'll get a chip with this circuit on it. And then the really neat thing is you get every single circuit. So you're going to get my project too, and I'm going to play with like everybody's project basically when I get these chips.
Okay, so
So
so before we finish, because we only have very little time now,
yeah.
uh, show a little bit more behind this. So where or how would you upload it, or do you need to register somewhere? How you can get these boards? How you get can anyone get these boards with these silicons or and play with these
Well,
circuits, even if they didn't design anything on the chip?
that kind of depends on how many we have left over. So yes, every time there's a tiny tape out run, I'm trying to, I'll load this in this window here. Every time we do a tiny tape out run, we get a certain number of chips. And that number doesn't necessarily equal the number of people who submitted a project. So we can have some left over. And in those cases, you can get a chip that you had nothing to do with. Some people reserve a spot and don't fill it, or reserve a spot just to be sure to get a chip. But in essence, often you can get one. So let's see, tinytapeout.com. What was I going to do? Oh yes, GitHub. I'm trying to do this in this window here, but I've never used the browser here, so I have no bookmarks. Tiny Tapeout. So in Tiny Tapeout, you've got so many repositories. But if we look for TT07, which is the current run, you have different templates. So if you were going to do a digital design, you'd take this one. There's an analog one here. Oop. So this template is mostly empty in the case of the analog. I mean, there's some stuff, but the point is your job is to change the docs so that you document your project and put in the GDS and left files that it requires. So what you do is you fork this or you use this template. It's a template, I think. I'm not logged in.
Yeah, it
But
says
anyways.
template, project template.
Okay, good. So you use this template, you put in your files, you push them, and the point is there are GitHub actions here that do all the things that you need to happen. So that's it. And then, okay, it gives you a green check mark. You passed all the LVS, all the checks, all the DRC. From there, it's just app.tinytapeout.com. And that's it. You sign in with GitHub, and well, maybe you want me to share my actual window because with my browser.
It's up to you.
That's it.
If you like, you can share it. But so you don't have to even register. Only what you need to have is your own GitHub account.
Yeah, that's it. That is. I'll show you for real. Yeah, give me 2 seconds. Brave. There we go. Okay, so you see this, right?
Yes.
Okay. So I am currently logged in. These are projects I have submitted. If you look at the WOA, that's my last one, and it shows you basically, okay, I'm here. I'm this blue box here, and I have project number 265 and da-da-da. When I submitted it, I basically, every time I made a change, it would run the actions. And when I was saying, okay, this is an update that I want to do, I would just tell the system, and it took the commit in question and said, okay, it's merged. And then, you know, at some point we hit the deadline and I couldn't merge new changes, but the point is it's done. Anyone can go to app.tinytapeout.com and just sign in with their GitHub and say, this is my repo, and that's it. There's costs involved for the tiles. If you want the demo PCB, I made those PCBs there, and you can get that, or just a chip. Or for schools and things like that, you could have one demo board and all the projects on that one chip. So then you're not paying, you know, the overhead. You just took multiple little tiles. So there's a lot of options. The point is, I've done a few projects so far, and it's really neat. Like this one was 8x2 tiles, but most of them are small.
So, but where did you order the board?
Oh, in here. Basically, when you're reserving your place, even if you don't have a project ready, you can reserve a spot, and you say, I want 2 tiles and a PCB. Pardon?
How do you do that? Where do you do that?
Oh, here we go. Let's show you. That's okay. It. So Tiny Tapeout 7, I want I want 4 tiles, 3 tiles, 4 tiles. There we go. And then here's the pricing for the tiles and the PCB. And that's it. I agree to this. Next. There we go.
Oh, okay.
So you're basically doing that here, and then after that, it's done. When it comes out, it all gets shipped. We're currently shipping Tiny Tapeout 4 boards, and so it gives you an idea of the turnaround time. We're shipping 4 now.
So who is behind Tiny Tapeout?
The short version is Tiny Tapeout. Zero to ASIC, the course, is Matt Venn. Tiny Tapeout is Matt Venn and Uri Shaked. Uri is Walkui. It's all kind of interconnected. Everybody works together on many different things. So in essence, yeah, the important thing is to actually, I will show that because there are some links that I would like to show.
Yeah. And so, and how the tiny tape out make this happen? Like, Matt is somehow connected to who is going to manufacture it. I have no idea.
Yeah. Oh, well, that I will share the browser for. So Tiny Tapeout arranges these chips, but who's making them? Well, that's eFabless.
Hmm.
So eFabless has a chip ignite, which is basically for $10,000 or something like that, you can get a chunk of wafer and put whatever you like in it.
Hmm.
And so Tiny Tapeout takes a chunk of wafer and then chops it up into chips that each have all the projects. So eFabless is the one arranging the shuttle, and then Skywater makes the chips. So there's a huge chain, and it's really interesting because everyone's learning here. The first MPWs through Tiny Tapeout, well, through the course and through eFabless, didn't work for various reasons. There were troubles at the beginning. It was tough. And so Matt, when we were doing the Zero to Analog ASIC course, the beta, he brought in Harold Predel to kind of answer our questions because we're doing stuff, but everybody's like, this is new. And so Harold's like a super expert, and he came in and basically consulted on that. So there's Harold, there's other universities, there's Matt and Yuri and Tiny Tapeout, there's eFabless, and then there's Skywater. And Google was in the mix for a little while, but no longer. They kind of moved out of that because whatever. And so there's a big chain of people, and it's getting to the point where now it's kind of it's done. These things are
Hmm.
coming out and they're working.
Cool.
So
Because, yeah, sorry for interrupting, but because, I wanted to add, because it's not only the space for people, but also there is circuit around this space which has to manage all the switching between these small specific cells and everything. So this much bigger circuit which is used for debugging and accessing these small cells, this was somehow created by someone before, and this is just reused by Tiny
well,
Tapeout.
originally, it was the Caravel. Caravel was like a pad frame with a little RISC
Hmm.
processor and stuff like that. And so that has the pad ring and the logic analyzer and things like that. And so Tiny Tapeout was in the user project area. And that kept on going for a little while. Then Sylvain Minot, TNT, did the MUX, so he's involved in that, but it was still in Caravel. Now Caravel is gone. We're using the open frame pad ring. And so basically we're getting closer and closer to being our own chip, but that's all developed by Tiny Tapeout, basically, all that surrounding
Hmm.
stuff that chooses between the projects because there's a MUX there. Now, two kind of MUXes really, but one is digital and one is analog. And you say, hey, I would like to talk to project number 265. It shoots all the IO to the correct project. Power gating turns on for if it's analog or something like that. So all that infrastructure is basically what Tiny Tapeout has done on top of all the actions and the
Okay,
infrastructure to make it
okay,
easy.
finally I understand everything. Because when I created the very first video with Matt, it was still the Google and it was still the carousel, exactly what you mentioned, and all these things. So yeah, there were some changes, and it's becoming kind of more straightforward because you just go through this Tiny tape out directly to the uh, other company, I forgot, and then manufacture it. So you don't need to like, the 7 months is the process, how long it takes to manufacture it. No, I think it takes like 3 months, or how, I don't know how many.
It it depends how much money you have. There's a thing called a hot lot where you basically say, hey, excuse me, I need to go to this step, and then your chip basically goes through all the steps one after the other.
Hmm.
But in order to optimize the process, there are hundreds and hundreds of steps. So your wafer, your project is right here. It goes through, injection of this or etching of that, and then it goes on the stack, and it sits there for a little while. And then, okay, you're doing step 4, and then it sits there for a while, and that's why it ends up
Because you are
taking
only
six
paying
months.
$10,000.
That's right. Yeah, that's a good part of the reason because then someone else comes by and it's like I'm in a big rush, and he bumps you over, and then you're just waiting longer. But in the end, it's actually been going faster lately. I'm not going to make any promises on Skywater or eFabless's part, but things are starting to move along. And Tiny Tapeout has started coming on a schedule. Tiny Tapeout 7 is about to end. A week later or something, the submissions will be open for Tiny Tapeout 8. So the idea is to have multiple runs always going on, going on, going on. And then because you're iterating, I did a few projects where I did one thing and then I I've improved it and then, did another submission, but I'm still waiting, still waiting. So
Okay, okay, so
there's
I
some delay
understand. So
there.
basically, Tiny Tapeout will be waiting until they fill out all the cells or sell all the cells, so they have enough money to, they don't need to,
No,
no?
it is hard set because it's related to when eFabless does the shuttles.
Mm-hmm,
So this date, if it's like the last one was 100% full, okay, that chip was packed. But if it's not packed, it's going anyways because
mm-hmm.
everybody who did submitted. So,
But then will they have enough money to cover the manufacturing expenses for the manufacturing?
that's the game. But so far it's been working out, and with all these new capabilities and the awareness, people are playing. And ideally, what I'd like to see is schools being involved,
Mm-hmm,
classrooms and stuff, because in that case it can cost them relatively little because they don't need 30 boards for 30 students, and they can basically have a bunch of tiles for each student. Everybody can do, teams or individuals have their little tile and play with even a smaller number of chips.
mm-hmm.
So, but yeah, so far it's been pretty fantastic. I mean, that last run, I think it was the first time it was 100% full. But if it's not full, we put in tests of this or a repeat of that, a little improvement, stuff. And Matt fills it up with other things.
Okay, okay, now I understand. So, would you like to also say something about yourself and what do you do and how, I have no idea. Like, what do you do
Yeah,
in your everyday job?
this is lots of it. Basically, my name is Pat Deegan, and I'm the co-founder of Psychogenic Technologies. And basically, we do, bread and butter PCB stuff is what keeps the lights on. So IoT and everything from design and architecture to prototyping. Because I have a little pick and place machine, we can do small runs for prototypes and things like that. But my interest has been captured in this past year or so by all of this stuff.
It's
So I've been playing more and more with Matt and Uri on Tiny Tapeout. Those demo boards and things that come out. I mean, I made those. So in this world, everybody's doing lots of different things and collaborating in lots of different areas, and it's kind of interesting. And that's basically what I've been doing. Oh, and I'm doing talks. I'm going to Portland for Teardown. I did Latch Up. There was, so I do these conferences, and that's basically to spread the word because I think this is really cool. And the fact that I said this in my last video about this stuff. It really is like the internet a few decades ago. Now, with everything being opened up, you don't need anything to participate. It used to be the barrier was hundreds of thousands of dollars, plus the expertise, plus all that software and the licensing and the general nightmare. Now we can play. And when we can play, we play together. And when we play together, it just explodes. And this is why I think it's the best time to get into this. With Tiny Tapeout saying, yeah, the door's open. You can actually have physical chips. Just think about what you could learn or what you could try out where it was impossible before.
yeah.
So
I think what is happening is what happened to PCBs because, like, I don't know, when I was starting with electronics 20 years ago, making PCB is so expensive.
oh yeah,
Now
do not think 4
it's
layers. Are you crazy?
now it's
Now
nothing. Like,
it's
wow.
amazing.
And also, chip. There is future in the chip design because now every country would like to, design their own chips because everyone is worried, like, what is inside of these chips inside of our phones. And so, as you know, like many countries are going to put a lot of money into these chip
There are
designs.
huge of cash in this. It's crazy. And there's a demand for people who are able to do it
Exactly.
that
Exactly.
cannot be met. It's like we need some people. I've worked with a company here on unrelated things. They do really cool backscatter technology. It's really neat stuff, and it's one of the reasons I started playing with ASICs. They were taping out their own stuff, and they were looking for analog engineer, and it was almost impossible. You pay LinkedIn big bucks, to have worldwide coverage, and you still can't find them. So hey, if you're curious, come and play. It'll either be fun or it'll launch a career because boy, is it needed.
Okay, thank you so much, Pat, for preparing all this. And if everyone is interested to learn more, they can follow your videos on your channel, and maybe they can even contact you and go
Oh
and
yeah,
have
get
a
in
look
touch.
on
And
everything.
I would like to invite everyone to come over, even if you're not taping out right now. There's on tinytapeout.com/Discord is the Discord server. And there's people with 20 and 30 years of expertise there, just there to share what they know. So if you're curious, come on down or, watch my videos. I have an ASIC playlist and contact me, reach out.
Okay, thank you so much, Pat.
Thanks a lot for having me, man.
And that's everything. Thank you very much for watching this video. By the way, we are preparing some very interesting tutorials, so if you don't want to miss them, hit the subscribe button. If you want, you can also check out our FedDevel online courses, where you will find everything important from basic board design up to advanced hardware design and PCB layout. The link is in the description. That's all for this video. Thank you again. Don't forget to leave your comments and see you next time. Bye.